Hello guys and welcome to my channel. Today we're going to be going over parallelized Monte Carlo simulations using geometric Brownian motion, which was a part of my capstone project for a class in parallel computing. And we're really going to be looking at two main issues. One being programmers hunt for more floating point operations, and the second being trying to hide latency depending on the type of architecture that you're using. So what we're going to do today is we're going to essentially go over the formula, some high-level assumptions, changes that I made to my formula to make it work for my use cases, and then runtime results and a little bit of a discourse on what happened. So with that, let's just jump right into it. So the problem overview is essentially I aim to implement a parallel geometric Brownian motion algorithm for forecasting asset prices after t time steps using a continuous distribution. Utilizing Monte Carlo simulations. In the example we're going to see, 10,000 simulations are done. And parallelism is implemented over the simulation paths, an algorithm to predict asset price after t time step. So obviously, with any type of predicting asset prices, mainly on this, I focus on stocks. Stock prices are very noisy. There's short-term fluctuations that can drastically trigger calls and change positions. The prices change every second, and there's opportunities within micro strategies within the long-term window. So, what is geometric Brownian motion, right? So, from a high level, just defining the variables that we're seeing on the screen, S is going to be equal to our asset price. Mu is going to be equal to our expected return, commonly said as risk-free rate. Sigma is going to be our variance. T is going to be our time step, so our change in time over our period. Uh, and Z is going to be our standard normal variable. Some of the properties of this formula is that S of T is going to be independent of S of T at the last time step. So every stock price is independent of what had come before. And then T is continuous and non-discrete. So not too hard. We can see here if we just keep flipping through, it's really just a two-piece equation consisting of one element being the drift and the other element being diffusion. So drift is driven by the expected return and volatility. And we're going to go through each of these more in depth. But just from a high level, it's more driven as expected return and volatility. This is the deterministic piece of Brownian motion, geometric Brownian motion. And this is the stochastic process that defines geometric Brownian motion, which would be diffusion. So we're drawing from a random normal variable distribution and essentially scaling over time with respect to time and volatility. So high level, if that didn't make sense, let's look at it like this. So in a discrete example, let's say we're flipping a coin and say, these represent whether we got heads or tails. Over the long run, right, we would expect to see a normal distribution. This is often called a random walk or equal probabilities. But we would expect to see a distribution of zero, mean zero, standard deviation of one. Um, what the people that had developed the Wiener process, which is also known as typical Brownian motion, had discovered is that as we scale for a continuous time series, we need to be taking our normal variable multiplied by our square root of the change in time, and that is scaled by volatility. And that is essentially our full diffusion term. It's pretty simple, just essentially a normally distributed variable that's scaled by the square root of time and volatility, um, giving us a stochastic process that decides where we're moving. The other piece is obviously drift, and it's a lot simpler. It's the expected return, so mu of asset, minus a small Ito calculus correction for the variance, and scaled over time. Those two are combined with an addition and an exponential to essentially create the geometric Brownian motion formula that you see today. So here you can see the closed form parallelization format that we're going to be using to parallelize across nodes um, and threads. So S is going to be equal to S times by um, the exponential of the drift plus diffusion terms, where this is what we were seeing in the past. And just as a note, this formula can be used to solve for t time step and does not need to have the full path generated. You can just solve for whatever time that you're looking for, whether it be half of your time period or the full time period. In addition to this, one thing I did try to implement was using pre-computed z-scores. So rather than, if you can see in this formula, rather than having to recompute this normal variable every time that this loop iterates, uh, we can just set this loop z to equal to a length of n and store that many random variables to try to speed up computation. So I'm not going to go into the code here. We can just look at the code on my laptop. Yeah, here we are. And we're just going to show, obviously, two things really quickly. So one, the geometric Brownian motion formula, which is here we're just getting our time step, our initial asset price, and we're iterating over time step n, computing the z, not our z array, but essentially one normal variable, and then doing parallel accumulation over S. Monte Carlo simulation is obviously just another for loop wrapped around it. So over m iterations, we're going to be calling GBM. So m is equal to 10,000 in this case, and we're essentially just going to be accumulating the final price into our partial sum and our partial sum square and printing out the average final price after 10,000 Monte Carlo simulations and then the standard deviation of this. In this example that we're looking at here, we can see that we have implemented a parallel block in between the Monte Carlo simulations. So this essentially just uses multi-core parallelism to parallelize across the threads that we're creating. So in this example, we're setting the number of threads to be equal to 8. This is set like this just because of the way I was running it in the cluster and the way that you have to submit your slurm script. So num threads would be equal to essentially number of CPUs. But in this example, you can kind of see, where we're going with it, just setting the number of threads to a constant amount, and then running our simulation across these threads. The only difference in the serial version is that we're not implementing this parallel region. Jumping over to the CUDA version is, again, not much different. Obviously, we have our device arrays for pre-computed Z normal values, our device results array, and our device squared values. Here handles our indexing of the past. So let me just jump, actually, make more sense. So when we're launching our kernels, we're launching with 256 threads. And here's our indexing formula for how we're going to index that. So we're essentially making sure that we're creating either m times n threads or m threads, and making sure that if we have any threads that are greater than that, we immediately return otherwise. And for every thread that is less than m, which would be 10,000, we're essentially going to compute the trajectory or the path for Brownian motion. Following that, essentially we just copy back the results to the host and aggregate the results on CPU and print out the results. So the CUDA version is, again, not much different, just essentially making sure the bookkeeping is correct with indexing and copying over the device arrays where needed. But let's just take a look at the results of this, right? So what actually happened? Let me present here, jump to my slide. So what actually happened over this? So I ran the test over doing geometric Brownian motion over a 1 month time period in minutes. So our n was going to be 8,190 total time steps and 10,000 iterations. And all the tests were done in double precision unless otherwise stated. So in our serial example using essentially a classic desktop PC CPU, we see that we ran our serial example in around 4.67 seconds. Our OpenMP parallelized version over our 8-core 16-thread processor, we see 0.78 runtime, and my laptop is not GPU accelerated, so we did not test. Compared that with the NJIT cluster, which is my school cluster, which runs in Intel R Xeon Gold, which is running at 240 gigahertz, which is 1.2 gigahertz lower than my AMD Ryzen. You can see the difference in speed, or the speed slowdown versus a more modern desktop PC. Clock speed wins in this example. Uh, Taking a look at the CUDA examples, so the Jetson Aura Nano is just a personal computing device that I run on my own, and the Wolver clusters obviously has high grade A100s. What I noticed was that the Jetson Orin does not have enough FP32 cores to run this algorithm in a GPU accelerated way. The pre-computed array ends up causing cache misses just due to the size, given the memory architecture of the Jetson being a lot smaller, and not being able to handle that. So I did make a small change and dropping precision to floating point or FP16, and also computing the z-scores in flight to reach the fastest GPU accelerated runtime that you see with double asterisks. On an A100, you can see that we can really hide this latency with the number of flops that the A100 is able to push, where I wasn't needing to make any changes to precision or the algorithm um, directly inside the terminal just due to how fast it was able to run. I was able to hide some of that uh, more than less optimal code. So taking a look at runtime, so runtime is essentially just plotted on our y-axis, and x-axis is essentially going to be our three different types of processor styles. So the AMD Ryzen 3700X, our Jetson Aura Nano Super, and then our Intel processor in combination with our A100 GPU. And you can just kind of see, obviously the GPU accelerated versions, just taking a look at the CUDA versions, you can see that the A100 really is able to hide the flops and the heavy overhead of allocating and deallocating the Z array um, here, versus in the Jetson we really need to be extremely optimal in the way that we're handling our flops and stuffing more arithmetic operations within the algorithm and less memory accesses for the algorithm to do. So key takeaways. So the processor architecture really does matter. So knowing the types of cores that you have on chip, your memory hierarchy, and any other information that's useful to you as the programmer can save you a lot of time and headache. The example being for me was the Jetson not having enough FP32 CUDA cores, um, was something that I didn't know going in and would have saved me a lot of time and headache, and ways to set up the program for this type of scenario. Um, Higher clock speed wins regardless of the array overload. We were able to see this demonstrated within the AMD processor versus the commercial Wolver, cluster processor. The higher clock speed still wins. That may be due to something with the way AMD handles their memory hierarchy and memory allocation, or otherwise, but in general, the higher clock speed is essentially what I'm attributing to the win on runtime. And obviously, stronger processor hide all these issues. So the A100 was running fast regardless of the memory access bloat between the pre-computed Z array. Um, it can hide the latency just due to having more gigaflops per second, um, but would essentially cause an issue running on further and further, larger and larger problem scale. So, like I say at the bottom here, at my current problem scale, we could afford some of these issues, but in practice, running simulations on an entire sector or index can be costly. So, as a continuation step of this, you should really be choosing a closer underlying distribution, which I didn't mention, but definitely look into that if you're interested. with also implementing rolling, drift, and volatility, which is a continuation of the first point. A complete removal of the pre-computed z-score distribution. Um, that should not be done on chip, and we should not be handling an allocation of m times uh, n arrays of z-score distributions. It's too much. It's too much allocating and deallocating, and causes a lot of bloat depending on the processor. And then obviously fine tuning caching to the hardware. So one thing I did mention was padding the arrays depending on where they sit on the cache line to make sure that we're preventing against false sharing. So each thread can accurately read and write into our shared variable S, our stock price. I kept a lot of these things flat to keep the comparison between processors similar, um, but something to keep in mind if you're going to be doing this on your own. But with that, I'd like to thank you for watching the video. If you enjoyed, give it a like, give it a follow, and I'll see you in the next one. Thank you.